Remote. Lights, camera, action. Now the sun's out, which is nice. Mhm. Don't start with this, for real? Because I can't use this. This thing again. All right, so our remaining schedule, some big updates. The first one is that our final exam is not to take place during finals week. That is a school policy in the spring. So our last lecture class was to be April 1st, and then our final exam was going to take place on the following whatever day that would have been. So for Saturday was the 3rd, Sunday would have been the 4th. Monday is a reading day on campus. Just got the announcement in my email literally 2 days ago. So there are no lectures in any courses. You should not be reporting to any class. It's a reading day. If your professor tells you to go, you can actually say nope. Monday, Cinco de Mayo. It's a reading day, which is no classes. You are supposed to be studying for those hours for your final exams that will take place for Tuesday, Wednesday. And I thought that's when we would have our class, Tuesday that night. But it turns out for night classes in the spring, given like the graduation turnover and whatever, we have to give our final exam on the last lecture day. So new important update, final exam, April 1st. So take away the day I was out, the day that was lost due to the emergency on campus. We are definitely cramming. So this is more for me than it is for you, but we have pretty busy days. With that being said, another important note, next Thursday, I can't be here. I will have the video already posted by 4 o'clock, so it won't be something that you will catch up later on. So if you want to come to campus, to the computer lab, the video will be live, or not live, it'll be posted by 4, so you can use regular class time, and the topic will be matrices. Perfect kind of lesson just to kind of watch on your own, because it's pretty dry anyways, but very procedural. If you've never seen them before, it's a good opportunity for you to watch on your own pace, pause, take notes, and then just practice that out. But I'll remind us that a few times so not this week, but next Thursday, April 10th, there'll be a not in person, but the video will be posted by 4:00. So it's not like you have to catch up. Given that we're now short on time, I am definitely going to cut exam 3 down. I've already trimmed it. That's probably to your benefit. So it will not take more than an hour. It will be a 1-hour exam, and we will have lecture afterwards to go over those things. And probably the same thing with exam 4, but we'll talk about exam 4 as we get closer. So here is our remaining schedule. Nice and clear. Tonight is April 1st, and that's not a joke. We will get through not all of this. I already know that's overdoing it, but as much of this as I can. I'm not too worried what gets cut. Exam 3 is this week, this Thursday. It'll be a 1-hour exam. I'll talk about what's on there. Again, very structured. It's already trimmed down, focused, and it'll be a 1-hour exam. And then we'll have a quick lecture after on law of sines and cosines. That pretty much takes us through our trig, the most important trig stuff you need for calculus. Trig doesn't really go away though, right? So we will see it in some remaining sections here and here predominantly, actually in matrices as well. So probably the newest stuff, the true pre-cal stuff is coming into play. We still got to squeeze in exponentials and logarithms that I put off for a bit. And then something called analytic geometry. So still have time for a review, hopefully on the 29th. So I should really say catch-up review. But most importantly, exam 3 this week. I'll talk about that at the end of the period. Next Thursday, watch the video on your own time. But please don't put it off to the end because there's going to be a good amount of homework. Not going to lie. Good amount of homework to go with that. Then exam 4 and a final exam. So not much time left. Right.
Did you post this?
I will post that. I wanted to talk to you first in person to make sure that it was there for us.
Thank you.
I'm going to give that a little highlight.
Today,
Import a. I wanted to end too. I like you guys, but I just.
You don't have to come.
What's that?
You say if a teacher asks a student to come.
On May 5th. May 5th.
Yeah, you don't have to come.
It's reading day.
Who the teacher will ask
I would
student to
confirm
come?
that with the teacher, but you can probably push
I'm
back.
just joking, but no student will ask a student. Teacher will ask a student, don't come. Then they say, okay, I'm not coming.
Well, if they say you have to come, you can say I'm not coming.
Not me.
Yeah, all right. Onwards we go. Inverse trig. So where are we in our big picture? Last time we met, was it graphs of sine and cosine? Yeah. All right. Yeah, that worksheet stuff. And there was some homework there. I would have done a little bit more there, but it's okay. They would have just been extension stuff, and what we would have just built on isn't foundational for calculus. So we're just going to creep forward. We did not talk about the graph of tangent, but I'm going to include that here. So I've made some modifications, and off we go. So inverse trigonometry. Do you guys remember inverse from earlier this year? Yeah? Inverse? What's inverse?
You just will typically start with a negative and you flip it about the x-axis.
Okay, so thinking in terms of symbols has something to do with a negative.
You flip the sign of x.
How about
Hang on, there's a lot being said there. Come back to you in just a sec. So what were you saying? Give me an example. Can you give me like a concrete example?
So we can say like negative, actually no, it'd be cosine and then negative x. I think.
Okay. So what triggers inverse to here? The negative sign?
Yeah, the negative side.
Okay, so you're warm, but you're not 100% correct. So inverse definitely has a negative sign in its symbolism. This is not inverse cosine, though. This is, and you said something. You said it's like a reflection. So that's what's going on here. This is like a reflection of the graph of y equals cosine x. So it would just reflect on itself, and therefore it's not even really needed. But yeah,
This might be a little more elementary, but like if you notice the first three, you just gonna reverse the last three.
It's cosecant, right?
Yeah, cosecant. Yeah, you just you take.
you're so warm. Well, it's all good. Let's get them out. Cosecant x is 1 over sine x. All right, we're getting warmer, and actually this is the most common error made when thinking about inverse. So we're getting warmer, but I'm glad this one came up. I will still say this is not inverse.
Oh,
I was
it's not?
thinking so.
Oh, okay, because it is April 1st, so we'll let it
Yeah,
go.
exactly.
This really is just there. This is just not a reflection graphically. This is just like a rule. It's a reciprocal rule. We call it an identity, but that's just like a reciprocal fact. So, all right. Hashim, what'd you say?
Output, switch to input.
Hey, all right. So an inverse takes, so for instance, if I have a rule that inputs 3 and then outputs 5, we can think of that as like a function machine. 3 comes in, something happens, and now 5 comes out. The name of that machine is f. Then this machine is going to take the output, make it the input, and then undo whatever happened. So it's going to, okay, just like that, undo my whole set of notes. Oh, that's too bad. All right, all right. Now I got like 4 copies of everything. Hey. So 3 comes in, something happens, 5 comes out. We call this machine F inverse. So there's your -1-ish, but it's literally just a symbol. That means we're undoing this machine, this rule. 5, we undo it back to 3. And so we're stressing this output, this range value becomes the domain value. And this domain value becomes the range value. Yeah. So that's what an inverse is. Cool. All right. Sine takes an angle and outputs a ratio, basically y over r. And if you're on the unit circle, it outputs the y coordinate. So inverse sine takes what? It takes the ratio and gives back an angle. Awesome. So where we see inverse sine tonight, we're thinking we need an angle whose sine is that ratio.
Excuse me, sir.
Yeah.
If if we look at the ratio y over r, why is it the inverse cannot be r over y?
Because that's a reciprocal, not an inverse. That's why it was good to kind of go through those things. Most common is right there. Right. So it just means to undo. We're switching the outputs with the inputs and the inputs with the outputs. We're not reciprocating. I will detour for a quick second. You're not coming up with this out of nowhere, because you were taught like this exponent does not mean inverse. Actually, there's an interesting story, and I'll try to keep it to literally 45 seconds because we are short. So you're thinking this, And that's what you're thinking this.
Yeah.
Yeah. And that's a reciprocal.
Yeah.
And then we come over here and I say, not reciprocal.
Yeah.
Terrible notation, but not reciprocal. It's literally the same symbolism, but it does not mean 1 over like any flip. It just means interchange inputs and outputs.
So can we swap the notation from -1 power to b power?
We can, but this is also super commonly used too. And furthermore, okay, this is like Jeopardy trivia. This actually is inverse because it's the undoing of multiplying by 8. And that's wicked mathy, but if you've ever learned in elementary school, and you did learn this, they were called like associative properties, commutative properties, but then you were taught that like 8 times 1 over 8 is the multiplicative inverse. There it is. 1 over 8 is the multiplicative inverse of 8. So the word inverse is kind of somewhere in there, and that gets really, 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 really muddy for the most general population, and it's not a disrespect. This on a number means a reciprocal. When you have that symbolism on a function name, whether it's sine or f or h or g, it does not mean 1 over. It means the undoing of whatever the actual function is. So it is a common misconception. That's, again, going back to 10 minutes ago, I'm glad you brought that up because it is super related, but not the same. All right, David said something that I'm not going to forget. But let's answer this right now. So sine of an angle gives a ratio. Therefore, inverse sine takes a ratio, and we give back an angle. So let's answer this question. Inverse sine of 1/2, that's a ratio. What's the angle? Nope.
45.
Nope. That's, you said it in radians, you said it in degrees.
Oh.
We are undoing.
If you have your unit circle anywhere nearby,
Yeah.
that may be helpful as well.
Unit circle.
Unit circle,
Yeah, what?
pi over 6. That sounds good.
5 over 6. 5 over 6. 5 over 6.
So if we look at our unit circle, we're looking for y coordinates that are what y coordinate has 1/2? Well, this one right here. Root 3 over 2, comma, 1/2.
But also,
You guys mentioned this a moment ago. So let me kind of clean up a couple things that's going on here. This angle is 45 degrees, which is pi over 4 radians. So that's a complete. You both kind of say the same thing in different languages, and they're both. But I like wrong answers. I really do. This angle if I drew it more accurately, just quick sketch here, is 30 degrees or pi over 6 radians. So we give the ratio 1/2. So let me say this. We would say the sine of 30 degrees is 1/2. Therefore, inverse sine, switch your output, switch your input. But, go on, David. But
there's another angle that also has a sine value of 1 over 2.
pause. What's that other angle?
150 degrees.
150 degrees. What about this guy over here? This has a negative root 3 over 2, but a positive 1/2. It is also true that sine of 150 degrees is 1/2. So inverse sine of 1/2 is 150 degrees. Okay, now we have a bigger problem. A function is supposed to take an input and give one and only one output. Inverse sine of 1/2, you're only allowed to say one thing for it to be a function. And we can't do that. So we have an issue. But we knew that all along. Now we're really thinking. We talked about inverses in this course. Go back in your notes, watch the video that I recorded. If a function passes a horizontal line test, then its inverse is a function. Then we can interchange x with y and y with x. What do we know about the sine graph? Does it pass the horizontal line test? No. It's a wave that goes on and on and on and on forever. So we right now have to make a decision. We have to make a decision. I hope we get it right, but if we don't, I'll just recorrect you. Let's look at a sine graph. That's a terrible sine graph, so don't look at that. Crest, trough, crest, trough. Okay, it should be completely symmetrical, but the vibe is there. It fails the horizontal line test infinitely times. But let's make it past the horizontal line test. Let's start chopping stuff off so that it passes the horizontal line test.
Cut out negative values.
All right. If we did that,
And we
well, here's why this is. Here's 30 degrees. Here's 1/2. Here's 150 degrees. Here's 1/2. So, all right, we have to make a choice here as well. I don't know about you. I feel like if we want to choose, well, I'll let you guys. Do you want to go with bigger numbers or smaller numbers? Yeah, so the mathematicians. So kind of using what David said here, let's now chop it up to this turning point. Where's the color? So now I'm just going to go up to there. What's this value? 90 degrees. Now here's a problem. What if I wanted to know negative 1/2? If we only say, all right, this now is part of a sine wave that passes a horizontal line test. However, we cut out too much because sine values, y coordinates can be negative. So if I was like, yo, what rotation gives me a negative 1/2, there's no negative outputs here. Like there's nothing at all. So how can we amend? How can we get this all beautiful in one single swoop? If we go from, I'll do this crest, and then imagine, I'll stop there, this trough backwards. And if we go from here to here, will this pass the horizontal line test? Yes. Does it capture every value in the range? What's the range of sine? -1 up to 1. Does it capture everything? The answer is yes. Right? Do you have a y coordinate of -1? Yeah, right here. Do you have the y coordinate of 1? Yeah, right there. 0, 1/2, -1/2, √3/2, -√3/2. And that's it. So I kind of guided that decision, but most times students will say, we kind of got there. If we consider the graph of sine, for each function, restrict the domain so that the function's either increasing or decreasing and as close to zero as possible. I'll do this nice and neat now. Up to here, from here, and just to be clear, like this is the sine wave that we're not including. We do want this part of sine that part of the sine wave from -90 to 90 degrees is now 1-to-1. It captures the entire set of outputs. And so, therefore, we can now say sine inverse of x exists. And its domain is -1-to-1, and its range is -90 degrees to 90 degrees, or -π/2 to π/2. And that's the backbone of the inverse sine function. We went through a lot, and we went through some misconceptions about what inverse meant, but we got to it. We stressed that this is an angle. I'm sorry, this is a ratio, and we want to give back an angle. So let's see if that's true. These are ratio values, and the outputs are angle values. Cool. So that's working as we want it to. And for it to work as a function, the original sine graph has to be restricted to that domain. We could continue this argument for sine, for cosine and tangent, and mess around, but I'm going to give it the quick version. Cosine, I still want a range from -1 to 1. Cosine starts at its max and ends at its max. Min. So there we go. Cosine, we will restrict from 0 to what's this value? When does cosine first reach its minimum value at a positive angle? 180 degrees, which is pi radians. So on that restricted domain, the inverse of cosine would exist. And the graph of tangent, if you've never seen it before, go to Desmos. It's not that exciting, but it's not a sinusoidal wave at all. Doing this quick version here. I hate that it does. I'm getting better, but still. Tangent looks like a cubic function. And there's one cycle of tangent. It has two vertical asymptotes. The reason being, if you take tangent of 90 degrees, I reminded us that the tangent is really the slope. Therefore, it's undefined. Similarly, tangent of -90 degrees is undefined. So this is -90. This is +90. And you could convince yourself beyond Desmos of some values here. For instance, 45 degrees, the x coordinate is √2/2, the y coordinate is √2/2. So you have a value of 1. But I like the argument that tangent is slope. So as you go to 90, the slopes are going steeper and steeper and steeper and steeper. And as you rotate towards negative 90, the slope of the terminal side is getting negatively steeper or decreasing even more. And you get that type of behavior. So there's your tangent. So tangent is already 1-to-1 on this interval. That's a lot. But that's everything that you need to know. The inverse of sine, the undoing of sine, David mentioned this 20 minutes ago, can also be called arcsine to avoid confusion. That's new and important. Inverse sine and arcsine are the same thing. They're the undoing of sine. They return angles. And those angles are between negative pi over 2 and pi over 2. How come? Because of the restricted domain. The domain that was restricted was sine between here, and its range was negative 1-to-1. So now when we look at its inverse, those switch places. Important, important, important. Here's how I think about it. When I see this question myself, I've just learned to say I'm returning an angle in either quadrant 1 or quadrant 4, because if you rotate to pi over 2 or to negative pi over 2, that's quadrant 1 or quadrant 4. So you're returning either a quadrant 1 or a quadrant 4 angle. And if it's in quadrant 1, you give the positive, and if it's in quadrant 4, you give a negative. You give a negative value. Inverse sine of 1/2. Knowledge of a unit circle is really important. This is a positive value. It's in between negative 1 and 1. Because it's positive, I know I'm in quadrant 1. So I just need to know my unit circle facts. What rotation has 1/2? We already answered that. 30 degrees or pi over 6. But if I was asked negative 1/2, then I'm just thinking, all right, what angle in quadrant 4, so down here, has a y coordinate of negative 1/2? And if you said 11 pi over 6, that's good, but you went all the way around the circle. We don't want to go around the circle. You just want to get to quadrant 4 moving downwards. So you literally just say negative pi over 6. And that's the answer. It has to be that. It has to be that. All right. So that's basically what I'm saying. When you're returning an angle, you're given the quadrant 1 positive, or you're given the quadrant 4 as a negative rotation. Inverse cosine returns either a quadrant 1 or a quadrant 2 angle. And that's because of what I've shown up here. Oh, I think I erased it. It's okay. Cosine starts at its max, and then when you rotate to the end of quadrant 2, it's at its min. So therefore, it's 1-to-1 on that rotation. So quadrants 1 and 2. Bottom line, if you are in quadrant 1, your x values are going to be positive. So when you're asked something like this, where is cosine root 2 over inverse cosine root 2 over 2? We're asking what angle has an x coordinate that's positive root 2 over 2. We're in quadrant 1. We would say 45 degrees or pi over 4 radians. But if you were asked negative root 2 over 2, don't rotate downwards. We're going to continue to rotate into quadrant 2. So 1 pi over 4, 2 pi over 4, 3 pi over 4 is the answer to that, or 135 degrees. Not easy, but once you're there, you can't really forget it. cannot stress enough. For sine, quadrant 1 or 4, cosine 1 or 2. These are the topics that will separate your understanding of calculus versus just trying to get by. Knowing this is the stuff that's coming up in this course. Everything really, but everything here is everything we've been doing so far is really just algebra. Now's the stuff that gets abstract. Tangent, I already said, is 1-to-1 from negative 90 to 90 because it's all the slopes. Your undefined, your negative slopes, your zero slopes, you got positive slopes. So therefore, it's very similar to sine. You return an angle between, and this is wrong, negative pi over 2 to pi over 2. I copied and pasted and did not change anything. And whose tangent is x. So basically return, very similar to sine, a quadrant 1 or a quadrant 4 angle. Inverse tan of root 3. We need an angle whose tangent is root 3. What are you thinking? Negative pi over 3. Correct. By the way, you can always check your answer. You can just rewrite this. Say tangent of pi over 3 is root 3. Right? So now switch these. That's what an inverse is. Tangent of negative, inverse tan of negative root 3 over 3. All right. Careful, I put a little spin on this. What is it? All right, so he's your study partner. He's got it. That's it. Can't stress enough. For it to function, it can only give back one value. All right. And for us to only get one value, we had to restrict the original graph so that they were 1-to-1. Give it a shot. So when I say I scale the test, like this question, when I put on a test, I'm like, you should answer all this within like 3 minutes tops, like tops. These are just like, these are all on the unit circle. By the way, this is not on this week's test. This is not on this week's test. This is the start of exam 4, I should say.
Can you go over like what's going to be on the exam?
Yeah, I'll do that at the end. First one, I think we've done at least twice already today. Next one. Next one.
0.
Oh. Yeah, that's what you said, right? And then what? Keep going.
Level 6.
How much? Did you say 5 pi over 6? You said pi over 6. Yeah, you said 5 pi over 6. There you go. All right, let's talk those out. Why?
Why are we not dealing with angle in this sense?
Huh?
Why are we not dealing with angles in this sense? Angle.
Angles.
Yeah.
We are.
Yeah.
We're talking about that in terms of radians.
Radian. Oh, okay.
Calculus, radians.
All radians, yeah.
Oh,
So we're trying to find an angle whose sine is 1/2. And when, for it to function, you thinking in your mind, well, if it's positive, it's got to be in quadrant 1. So where do we rotate to get a y coordinate of 1/2? Pi over 6. Right? This is how you should know your unit circle. Next one. I need a sine whose y coordinate is negative root 2 over 2. If sine's negative, graphically, all students take calculus, you're in 3 or 4. But inverse sine has a very specific function. It gives back this angle. You have to start at 0 and rotate clockwise. You have to say the quadrant 4 angle in this rotation. So how do I get to negative root 2 over 2? You rotate downwards, pi over 4, negative pi over 4. Cosine inverse. We need an x coordinate that is positive 1/2. That's in quadrant 1. Now, I know the sine of pi over 6 is 1/2, so it must be its complement, so pi over 3, the 60-degree angle. Lastly, cosine is negative. That means x is negative. First of all, it's not here or here. It's either in 2 or 3, but for our cosine, it's a very specific return. It's the quadrant 2 angle. So we need a negative root 3 over 2. That's at, put myself on the spot here. Has a reference angle of pi over 6, so 5 pi over 6. There we go. Or 150 degrees. Tangent values. Oh, by the way, I'm just kind of, see, literally, they mean the same thing. Literally interchangeable. Root 3, so we want the quadrant 1 angle, and just know it's the bigger one. I gave that little trick, so this is going to be pi over 3. Arctan of negative 1, negative pi over 4. So it acts like sine in the sense that we either return quadrant 1 or quadrant 4. And basically, where do you get a negative 1 slope? Right in the center. Pi over 4, downwards, negative pi over 4. Where do you get a y coordinate of negative 1? Negative pi over 2. All the way on the negative y-axis. And where do you get a cosine of negative 1? Yeah, study with Hush. He's got what's going on there. Definitely got it. All right.
So I just want to make sure because when I saw the tan graph, it kind of made me think it was only the first, third quadrant. Just double checking. And when we're doing this for it, it's only the first and fourth, just like sine, right?
So tangent is slopes. And here's 1, and here's undefined. And these are positive. These are angles up to quadrant, like all through quadrant 1. And so those slopes start at 0, and that's a very small slope. Like a baby could climb that, and then most of us would probably just fall right to our demise if it was that steep. But my point is, it helps me understand that the slopes are just getting bigger and bigger and bigger. And then like when you're really close to 90, they're still continuing to grow, but they're massive. And so it kind of makes sense why the graph of tangent does something like that. It curves more than that. But to answer your question, what are these numbers? These are negative angles, which just means clockwise rotations. So if I go negative 45 degrees, that's a negative 1 slope, and negative 90, and long story short, when we look at that tangent graph, we're looking at angles in quadrant 1, in quadrant 4, but that were created by rotating clockwise.
So yeah, the same as sine.
It's the same as sine.
All right, that makes a lot of sense.
Once it makes sense, you like,
Slope can be that degrees.
yeah, exactly. Yep. Compositions. Woo, another big one. Bottom line. I want to be able to cross stuff out. That's where this is all heading. I want to just be able to cross stuff out. Because we're about to move into trig equations. And so if you have something like this, we're going to say the legal move is to take the sine of both sides. Or if you have something like this, the legal move is to say take the inverse sine of both sides. And so that way, the left-hand side will just become x. You'll see that. We're going to do that shortly. But there's a lot of little caveats that are going to come up. This looks overwhelming. This gives me anxiety, and I'm the one who friggin' typed it. But here's how I say this. I just have to talk it out, and pictures help sometimes. Inverse sine is an angle whose sine is this number. I just have to make sure that it doesn't exceed 1 and it's not less than -1. Otherwise, it's a fake answer. It's not even real. We'll see it in just a minute, okay? But that's what you have to remember. I want an angle given a ratio. That ratio can never be bigger than 1 and never smaller than -1. As long as it's in between -1 and 1, this cancels out nicely. We don't have to pay super much attention with tangent because we want an angle whose slope is anything. Can I think of a line whose slope is 0? Yup. Can I think of a line whose slope is 1? Yup. Can I think of a line whose slope is 1,000,000? Yup. That would be really, 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 really steep line. Can I think of a slope that's negative? Yup. So I don't have any restriction here. Slopes can be any values. No restriction. Can always just cross out tangent. When we spin this around, let's just come back to that one. That's where it really gets nasty. I need an angle whose x-coordinate is 0.7. Now, we can look on the unit circle as much as we want. It's not there. It's not a common value. But 0.7 does not exceed 1. So that board's a little bit of a mess. I'll just add a new paper. So visually, I need an x-coordinate. Here's an x of 1 right there. Here's an x of 0 right there. So is it possible to get an x of 0.7? Yeah. I don't know, right here maybe? X equals 0.7. So there's some angle. It's not a common angle, but there's something that does that. So sine theta equals 0.7. I don't know what that is, but it's there. Oh, cosine theta is 0.7. And now what does the question ask? Find an angle whose cosine is 0.7. There it is. And then it says, take the cosine of that angle. Take the x-coordinate there. You see how it's kind of just like canceling out? That's what inverses do. Find an angle whose x is 0.7. I did. It's right there. Okay, now tell me the x-coordinate there. 0.7. Silly. These cancel out. 0.7. Let's try to do that with the next diagram. Find an angle whose y-coordinate is 1.2. Well, here's y is 0. Over here, y is 1. Over here, y is -1. Over here, y is 0. Do you agree with all that? Where would we find a y value of 1.2? We'd have to go past 1. Wait, this is now shooting me back down here. Of y of 1.2 is not possible. You have to be like 0.7, but you can't be 1.2. You have to be in this interval. Then they just cross out. Tangent can be anything. Zoom, zoom, 4.1. because it's slope. Find an angle whose tangent is 4.1. So imagine 4.1. That's like 1. So 4.1 is probably like this. Okay, now take the slope there. It's 4.1. Those just cancel out. That's the idea. It's crazy how a little switch here will just get insane. My answer to this, and I'll go back to what's written up there, is sketches. Here, we're starting with rotate pi over 6 and take the y coordinate. Okay. What's the y coordinate of pi over 6? 1 over 2. Now, what's the inverse sign of 1 over 2? Pi over 6. That canceled out because this is a quadrant 1 angle. End of story. What is the x coordinate if we rotate negative 2 pi over 3? Wait, I'm thinking myself. Give me what's pi over 3 is the reference angle. Okay, so what do we think it is?
I think it's negative 1/2.
It is negative 1/2. Sorry, I was hearing root 3s, 2s, basically anything. So I was like, wait, what is it? Yeah, go to your unit circle, rotate that amount. Your x coordinate is negative 1/2. So what's the answer to this now? How much?
Negative 2 pi over 3.
We have to return an angle in quadrant 2. We have to. That's how that works. See? Gets tricky. Gets tricky real quick. So it'd be 2 pi over 3. One tip. What did I say we can do with negative signs inside a cosine? Just like factor them out and they fizzle. They go away. Didn't I say that? So if we did that with the negative first, then that would have been a quadrant 2 angle. What quadrant is this angle in? 3. So putting this all together, I said a sketch helps. Here's negative 2 pi over 3. And that's a warning bell that we just can't cross this out because inverse is got to be an angle in either 1 or 2. Right? So when you draw a picture, and if you know what you need to return, you can say, I better be a little cautious here. I have to be cautious. Right? Then there's so many different ways to think about it, but I gave you one. Factor out the negative sign, and in cosine, it just fizzles away. What's that? Just for cosine. What happens if you had a negative inside a sine? It's still negative. Yep. And that's what I'm saying right here. If you have a negative inside, just factor it out and fizzle it. Here, it becomes negative. Cosine is even. Yes. And sine is odd. True. See if you can come up with this one. Nope.
Negative square root 2 over 2.
Nope.
Negative pi over 4.
Correct. But you guys said some stuff. This inside value is, if you know your unit circle facts, what you said, negative root 2 over 2. But this has a very specific rule that says give the angle, it can't be in quadrant 1 if sine is negative, give the angle in quadrant 4 where you have a y coordinate of negative root 2 over 2, and that's negative pi over 4. So you're warm with that, but it was just incomplete. I don't know, maybe that's what you were answering, not the whole thing. There's other ways to get there, but basically make sure you don't just cross things out. What this is saying is, if that's in between negative pi over 2 and 2, like if that was an angle here, then they cross out. Otherwise, use some caution. I don't want to go much crazy. I will really focus in on these top two. Taking out the negatives can sometimes be the most helpful thing. And if that original angle was a quadrant 1 or 2 angle between 0 and pi, quadrant 1 or 2 angle between 0 and pi, then those cross out. As you go through your homework, which your homework for the next 40-ish hours should be study for the exam. But after that, when you start getting into the stuff, basically just work carefully, right? Work carefully. Sometimes you can just cross things out. Sometimes think about the inverse trig. We do have to move on. I know we're all not there. I just get the vibe, but it is what it is. If you're not strong on the unit circle, then it just gets worse. I'm not going to lie. So knowing your unit circle facts, as I said to do weeks ago, I think even before spring break, I was like, one of the best things you can do is practice the unit circle so it doesn't feel like it starts stacking up. So you can just see it in your brain. But if you don't have those down, that's your multiplication table. It's a house of cards. It's going to collapse. I'm not trying to be a jerk. I'm just a realist. Find the exact value of cosine arcsine 2/5. We need to return an angle in quadrant 1 whose value is 2/5. That's not on a unit circle, but we're going to sketch a picture. Quadrant 1 angle. There it is. And I need the ratio of y over r to be 2/5. 2/5. An angle whose sine, because this is positive, in quadrant 1 is 2/5. There it is. There's the angle. Its sine is 2/5. Take the cosine of that angle. I love this question. This is the calculus question. This is the calculus question. Actually, the next two are the calculus questions, but this is the less abstract version of your calc questions. An angle in quadrant 1, because this is positive, bing, bing. Take the cosine of that angle. We need this over that. How do I find this missing side? Pythagorean theorem. X squared plus 2 squared equals 5 squared. X equals root 21. So the answer to that is root 21 over 5. Write the trig function as an algebraic expression. Here's the calculus question. It's not really, this is still pre-cal, but this is what you need for calculus. We need an angle whose tangent is x. There it is. Tangent is y over x. Now we're really messing with our minds because that x and this. We need to make sure that the opposite over adjacent, that's cool. Now I have another way to think about it, is x. What should opposite be? What should adjacent be? Opposite should be what would adjacent be?
One.
Except, so what should opposite be?
Opposite should be one.
Opposite should be
They
x.
should all be natural numbers. I mean, not all of them, but
Do I have an angle whose tangent is x? Opposite over adjacent is x.
Yeah, x with y is x.
I know. That's where the symbolism is insane. That's why I switched the word to opposite and adjacent. So what we learned there's a ratio here. There's an invisible 1. And there's a definition for tangent, which is y over x. But now this x and this x are different x's, and things are getting really, really sloppy. So let's go back to another definition of tangent, which was opposite over adjacent. And that's more helpful. Opposite of this angle has to be x. Adjacent to this angle has to be 1. Take the secant of that, which means we want the reciprocal of cosine, which means we need the hypotenuse. X squared plus 1 equals r squared, the hypotenuse. So take the square root of that. Equals secant. I'm sorry, does not equal secant. Equals r. So at the end of the day, secant of this angle is r on top of 1.
it's not x plus 1 equals r.
Because it's over 1. What's up?
Oh, okay. I thought it'd be x plus 1 equals r because you take the square root of everything. Square root of x squared is x.
That doesn't simplify that way.
Okay.
Big no.
Yeah,
Nope.
but domain if you start taking square root of squares.
Okay.
It's because the sum. If it was factors, it works. But with sums, they don't simplify that way.
Okay.
Super common. I have like a little. Don't do this in calculus, and that's one of them. But yeah, that's my last lesson. You'll see. I have a cheat sheet for you to take the calculus. Don't do these algebra things in calculus, and that's one of them. Don't break that up as like x plus 1. I'll detour really, really quick. What is this definitely? Well, what's 9 plus 16?
25.
So,
Square root of 25, and it's 5.
so now, if your claim was true,
He did say it's before, yeah.
I don't know if I did.
Yeah.
I did. I know I did. I've said this a million times, but I don't know if I said it in this class. What is this definitely?
That's
3 plus 4.
It's not the same.
These aren't the same. So that means these aren't the same, which means these aren't the same.
Yeah. Okay. Thank you.
Matt, but it is, you are not stupid. Everyone makes those mistakes. Only math teachers don't make those mistakes because we did, and now we just know not to. But I did. I can't even tell how many times I made it. Cotangent of cosine of this. Okay, let's do this. We need an angle. There it is. What's cosine? We can say, I don't want to use x and y's and r's. So it's
Adjacent over hypotenuse.
so the adjacent is x. The hypotenuse is, and now we're going to take the cotangent, which is Tangent is opposite over adjacent, so we need adjacent over opposite, right?
Yeah, yeah.
So we need this. We need the opposite side. And then we're just going to stack it on top of x. How do we find that opposite side? Good old Pythagoras again. X squared plus this thing squared, come up with whatever variable you want, equals x plus 1 squared. That's not 0. I'll just make it like blue, how it looks like 0. Come up with a variable, probably a better idea, y squared, whatever you want, but just get, the variables can be mad confusing. If we expand this is x squared plus 2x plus 1. We can subtract x squared on both sides. This thing squared equals 2x plus 1. Hit up with the square root. And since we are in quadrant 1 and it's a side of a triangle, we will say it's the positive of this 2x plus 1. So at the end of the day, the adjacent side is square root 2x plus 1. The opposite side is x. And it turns out that this expression can be rewritten like that. I've mentioned a connection to calculus. If you've had any, because I know some of us have connections to calculus, when you take derivatives and antiderivatives, derivatives and the inverse of derivatives, inverses don't go away. It turns out finding some derivatives aren't that bad, but going the other way is really difficult. But if it's in algebra form, it's less difficult. So one strategy in calculus is to take complicated expressions that you're going to be differentiating and anti-differentiating and changing them, especially if they're trig, into algebraic forms. And then working with the algebra is a little less stressful, but not much. Still pretty stressful. No, I'm just teasing. Inverses. Biggest takeaways there. Right here. That's the biggest one. Second biggest one, right there. And then everything else is important, but if I had to name the biggest, all right, here, just be careful, all right? Go home, think about this again, read a textbook. If you don't like my lesson, that's fine. You guys are so lucky to have a million other professors on YouTube. Guarantee they're no better or worse, just different. It is tough. There's a lot going on here, but at the end of the day, this is an angle whose x coordinate is 0.7. As long as it doesn't exceed 1 or -1, it exists. Same here. This is an angle whose y coordinate can't exceed 1 or be less than -1. That's a problem. Tangent can be anything because it slopes. Switching that, we start on the inside. We want a y coordinate. If we rotate pi over 6, you get 1/2. Then undo that, you're back. Just kind of emphasizing that inverses and functions cancel each other out, but only if it's a quadrant 1 or a negative quadrant 4 angle. If it's not, just find the value and then make sure, for instance, cosine returns a quadrant 1 or 2, because this is a negative, it has to be 2. All right, and that's that. And that's your inverse topic. Import. Solving trig equations. Reason we talk about inverses, the undoing, is so that we can solve trig equations. So, next topic. Trig equations. Wicked basic. And none of these are calculator. Nothing. So, exam 4 will be 2 parts. Definitely no calculator part, and then you turn it in for a calculator part. Because the matrix stuff you're going to need calculators on. Parametrics and polar stuff you'll need calculators on. So exam 4 will automatically be part no calculator, part calculator. This is stuff you should know. This is a basic linear, well, it's not linear, but it is because there's no squaring, there's nothing fancy here. You're basically just saying collect all your sine terms on one side. So subtracting 3 sine x on both sides, we get 2 sine x equals root 3. And then we divide by 2, and we get sine x equals root 3 over 2. So everything I did there was isolate the trig function. Okay. Now, if that was cosine, or if that was tangent, or if that was anything, you isolate the trig function. That's how you attack these type when they kind of just, as we go through, you'll recognize the different types. Now, how do you undo sine? I'm going to be silly for a minute, just to emphasize the last lesson. Do we divide by sin? No. Those aren't unknowns. You don't do that. That's like saying if f of x equals x squared, divide by f, and x equals x squared over f. No, it doesn't even make sense. You never done that. It doesn't make sense to do that. This is like a function name. It's not saying anything. It's not a variable times a variable, all right? It's a function name. You don't divide by a function name. That just makes no sense. So you don't divide by sine. You don't subtract sin. Well, how do you get rid of sine? You use its inverse. You undo sine. So you literally would say, take the arc sine of both sides. Bless you. Now, we assume that this is working nicely. We don't have anything else. We don't have any other reason not to. So arc sine of sine cancels out. We're left with x equals the arc sine of root 3 over 2, which has what value? Pi over 3. Cool. Is that every single angle that makes this equation true? And it turns out no. Okay. First, anything coterminal with that also makes the equation true. And if I can really quickly, even if I can't, I'm going to try. I had this ready just to emphasize it. Yeah, of course it got lost. Uh, 5 sine x, 3 sine x plus square root 3. And where they intersect are the solutions. So the first intersection, look at that, when x is pi over 3. What is coterminal to pi over 3? Well, if we add 2 pi to that, what do we get?
You get the next period.
2 is how much out of 3? 6 out of 3. So pi over 3 plus 6 out of 3 is, there it is, 2 pi away. And 2 pi away. Anything coterminal with that, these graphs intersect. By the way, remember, where 2 graphs intersect is a solution. That's like algebra 1 things. So they intersect there, and anything coterminal. However, what else am I missing? I'm missing this intersection and everything it's coterminal with. What do you think this one is? 2 pi over 3. Why 2 pi over 3?
Are you talking about the intercept?
Yeah, we just saw where they intersect. So I'm back to this. Here's like the algebra to this. 1, not all. 1 solution is pi over 3. I really should have gave myself more room. To find all solutions, we must A, add 2 pi to our answer over and over and over and over again. So we write pi over 3 plus 2 pi n.
2k pi.
Depends. You want to use k, n? Our textbook uses n. It's just saying this is standing for some integer. So you would just have to be super clear as a mathematician. We don't need to be that level of clear here. But this is just standing for an integer. So for instance, sub in 0, you get a solution, pi over 3. Sub in the number 1, that's just saying go 1 time around a circle. Go 2 times around a circle. Or go -1 here, go clockwise a circle. That's how we mathematically express over and over and over again. We write that symbolism, plus 2 pi n. All right. Secondly, we need human knowledge. That sign is positive in quadrant 2 as well. So this is saying, give me some rotation that has a positive y coordinate. We just spent the time talking about how this is built on a calculator and computers, and so that it functions, you only can give back one number. But then we come back to this idea that we know there are infinite numbers of answers. We know for this to function, we had to restrict some stuff. It's almost like we have to do the unrestricting now. We have to say, we also know that sign is positive in quadrant 2. So a sketch helps if needed. I mean, I can see it on the unit circle, but if you know your one solution is pi over 3, make that your reference angle, and this is your second solution, which is pi minus pi over 3, which is 2 pi over 3, plus 2 pi n. In closing, the solution, all the solutions to that equation are written as pi over 3 plus 2 pi n and 2 pi over 3 plus 2 pi n, where n is some integer. Again, just to beat it to death, because we're going to need it in like a second, n can be 0. That's a solution. That's a solution. How many solutions do you want? You want more? All right, sub in a number for n. Basically, just add another time around the circle. And I won't switch back to what's on this screen right here, but it's the intersection points. It finds all those intersection points over and over and over and over and over again. All right, next, solving something called multiple angles. Isolate your trig function. Done. This 2 is not outside the trig function. It's literally on the inside of tangent. So this is an inside multiplier. Unlike the last example where we had an outside multiplier, we can divide by it. You don't divide by the inside multiplier. I could make a silly story about like that whole f of x thing. We don't do it. Isolate your trig function. It's isolated. So we're going to hit it up with arctan. Sin r, sin r. We get 2x out. What is arctan root 3? You said that earlier. What quadrant is that? 1. I didn't mean to go that far. So this right here is quadrant 1. Okay. 1. But where else is tangent positive? In what other quadrant? Not 1, but quadrant 3. So we also need to say that 2x equals, we need a reference angle of pi over 3 in quadrant 3. What's that rotation? 4 pi over 3. In quadrant 1, tangent's positive, but also in quadrant 3. That was that whole conversation a minute ago. Furthermore, we need to add this is just not enough room, but how fast does tangent repeat itself? We haven't addressed that yet. David knows his stuff. Slopes are tangents. What type of slope is this? Undefined. What type of slope is this? Negative. 0. Positive. Undefined. Then what happens? You get positive and negative slopes again. But wait a minute. So for instance, where's negative 1 slope? Here. Where's positive 1 slope? Here. So when I go to quadrant 2, I already have a positive 1 slope. Basically, tangent repeats itself every 180 degrees. That's further emphasized right here. If you go beyond 90 into quadrant 2, you will get negative slopes until you get to 180 degrees where you have 0 slope. And then in quadrant 3, you have positive slopes. And then you're back at the beginning. So this graph repeats itself not in 360 degrees, but from negative 90 to 90 is 180 degrees, which is pi radians. So we don't add 2 pi to tangent, we strictly add multiples of pi. Now we divide the equation by 2. We get x equals pi over 6 plus pi over 2n, and x equals 4 pi over 6, which simplifies to 2 pi over 3, plus pi over 2n. And that would be all the solutions that work, okay? What's this thing? This is called our restriction. This actually is saying we don't want all the solutions. We only want the values that fall between 0 and 2 pi. So if n is 0, this is pi over 6, which is between 0 and 2 pi. And if n is 0, this becomes 2 pi over 3, which is in between 0 and 2 pi. If n is 1, this is pi over 6 plus 3 over 6, which would be 4 over 6, which simplifies to 2 pi over 3. That's also in between 0 and 2 pi. And if n is 1 over here, we need a common denominator of 6. So we'd multiply this by 2. We'd multiply this by 3. That would be 5 pi out of 6. Do I have that right? Yeah, 5 pi out of 6. Which is also in between 0 and 2 pi. Let's keep going. If n was 2, we would add 2 pi over 2, or I guess that's just pi, or 6 pi out of 6. So that would become 7 pi over 6. And if we add 2 over here, or substitute in 2 over here, this would be plus pi. So that would be 5 pi out of 3. And again, is this less than 2? 7 over 6 is less than 2. 5 out of 3 is less than 2. Keep going. N equals 4. This would be 2 pi. And that's our, 2 pi plus some more is going to exceed 2 pi. And if I sub in 4 over here, this becomes 2 pi. So if I add more than it, that exceeds it. So this equation has a total of 6 solutions. 6. 1, 2. Oh, are these repeated? No. Oh, it's twice. Okay, yeah. That came up twice. Repeated. 5 solutions. It's not wrong. It's just repeated. So all you would type in or just kind of recognize is that those graphs would intersect 1, 2, 3, 4, 5 times between 0 and 2 pi. So lots going on here with solving the equations. Again, we're still using arctan, which gives back one value, but we have to use our human knowledge that tangent is also positive in quadrant 3. So you use your reference angle to get that, or you just know your unit circle facts. You still write the general solution for all answers. When you divide by 2, you get that expression. And you literally just kind of sub in numbers of n until you exceed pi over 2. Everything that works, you contain. I will stop there since this isn't on the test anyways, and definitely didn't get as far as I want. Pretty close, almost there. My 10 minutes a little behind. We just have a few more equations to solve, but we'll do that after the test. So I know you're curious about what's on the test. I have it typed, and then I was going to use the typed version to tell you the topics tonight because I was tweaking it, and I'm still making some final adjustments. But first and foremost, it starts with I'll just do it this way. starts with rational functions. All right, so that was something we did not get into the last test. If you remember, it's been a while. This was right before spring break. So the only non-trig thing is rational functions. So you should be able to identify asymptotes, vertical, horizontal, slant, holds in the graph, intercepts. You should be able to, given characteristics, any of these things above, write a rational function equation. So basically here, I think there's like two questions. I'll leave it at that. And I'm going to say, boom, state all the asymptotes, classify them, write their equations. For instance, if you say something's a horizontal asymptote, it has to have y equals. If you write x equals, no points. It's that minor, but it's also, I'm telling you, a horizontal line is y equals. A vertical line is x equals. It is no credit otherwise. Holds in the graph. We discussed how to find them. Review it. I give you an equation. You can tell me what the holes are and the y values there. X and y intercepts. That was in the homework. By the way, slant asymptotes is when you're top heavy by 1 and you may need long division. You will need long division. I'm going to tell you exactly what to know. That way it's like, if it's wrong, I don't have to feel bad grading them. I don't feel bad really grading them anyways, but I really won't feel bad. I'll say, it's on the video. You will need these things. Given a characteristic. So I say, hey, here's a rational function. It has a hole, it has this vertical asymptote, and it has this x-intercept. You should be able to write the equation. You should be able to work backwards. So a couple questions where I give you the equation, you tell me the characteristics. Question where I tell you the characteristics, you tell me its equation. The rest of it's trig. And in a nutshell, not necessarily in the order we did it. What's up?
Is there any graph? We need to graph
No,
something?
no, you won't have to graph any irrational functions by hand. In terms of trig, 1, radians. Theta equals R over S. And the homework questions that go along with that. Convert degree to radian and back. Radian to degree. Two, angles. Standard position. Sketch an angle 600 degrees in standard position. You better show me something starting on the positive x-axis, rotating upwards beyond 1 time around. It has to look like that. It needs to say, I'm starting here and I can follow with my pencil the direction for a positive angle. If it was negative, it has to go clockwise. So these are very easy questions, and they're also very easy to not earn full credit because you're just trying to willy-nilly pay attention to the details. Upwards for positive, downwards for negative. You start on the positive x-axis. You end in a quadrant. There's a reference angle. And you should be able to tell me coterminal angles. Least positive, greatest negative. And by the way, this is for radians, and degrees. So I might say sketch, I'm going to say sketch something like 13 pi out of 18. And you should know right away that's in quadrant 2 with a reference angle of 5 pi out of 18. Mad simple. And if you don't know it that quick, you're going to run out of time on the test. Unit circle. You should be able to complete it 100% accurately. End of story. In 5 minutes. You don't think you can? I say this every time. Everyone goes home scared shitless, and then they come back and people turn it in 3 minutes. The first question you will get is a blank unit circle. You will have nothing else in front of you, and you will have no more than 8 minutes to complete it. I collect it after 8 minutes, and then I give you a 0 on it afterwards, and you have to remake it up. So know your unit circle. I'll give you 8 minutes to complete it accurately. After 8, you're going to start on the other questions anyway. That's the first question. Give the paper, turn it in. It's all or nothing. There's no partial credit.
So are you going to give us like a second test on the unit circle? Or are you gonna...
First question. It's going to be, everyone's going to say, don't flip this one sheet of paper over till I say go. And then you're going to say go. And then boom, you have 8 minutes to complete it. If you finish it quicker than that, you can have the rest of the test. And when I grade it, it's all or nothing. If you forget one sign, it's wrong. Complete it 100% accurately. Somewhere between 5 and 10. No more than 10. That's kind of harsh, but still, it's weighted. Trig definitions. So there's X, Y, R for cosine, sine, tangent, secant, cosecant, cotangent, and then there's SOHCAHTOA. You should know both of those. So if I say, what's the cosine? You know it's X over R. If I say cosecant, you know it's R over Y. And if I ask, what's adjacent over opposite, you know it's cotangent. So there's right triangle definitions, and then there's like stronger definitions, kind of circular definitions. They play well together. Things that we did with that. So given a point, for instance, -2, -3, state the 6 trig functions. So you have X, you have Y, immediately you have a tangent, 3/2. You also have cotangent, 2/3. And then you can sketch a picture. Just quick review here. You know it's in quadrant 3 because it's negative and negative. Boom. This is your X. This is your Y. This is your radius. It's not on the unit circle, but it doesn't have to be, right? Because we know the definitions for any values. And to find R, X squared plus Y squared equals R squared. Given a trig function. And info on the quadrant. For example, cosecant theta is -3 and tangent theta is negative. Find the other 5 trig functions. Cosecant of some angle is negative. Tangent is negative. sketch a picture to determine the quadrant, or all students take calculus. Well, first of all, we're not in quadrant 1 because everyone would have to be positive. Tangent's negative, so we're not in quadrant 3. And cosecant is the reciprocal, as I said, you should know, as sine. And if sine's negative, we're not in quadrant 2. So you know you have a quadrant 4, which means from there, you should be able to find all the trig functions. There's many ways to do it. There's pictures. I heard some people say, I'm just going to draw the triangles. I have no problem with that. Some people use the X, Y, R definitions. All good. Basically, at the end of the day, you should be able to find the rest of the 5 trig functions like you did in your homework and just make sure the SIGN, the positive and negatives, match up correctly there. So we have rationals, trigs, radians, degrees, angles, unit circle, right triangle. I got this test memorized.
Thank you so much for doing this.
I already had it ready. I'm going over time a little bit. It's all good. This is because you guys asked. You'll have this all at home. So if you need to take off, feel no need. I don't feel disrespected if anyone takes off right now. This is just added. Right triangle stuff. So basically, I already went through SOHCAHTOA, but really just getting to it, angles of elevation and depression. Word problems. There were some in math lab, there were some in class, and basically at the end of the day, know them. I mean, they all have a vibe that this is 0. If you look up at something, that's your elevation. If you look down at something, that's your depression. That concept's very simple, but then executing it and drawing the triangle and figuring out what you need can be pretty challenging. All right. A common question we did was something like this. Where someone's here and notices on the top of a cliff, the top of a lighthouse, I don't know, with some angle of elevation. Right, so they look straight ahead, 0. Then they go, oh, if I look at 21 degrees, I can see the top of the cliff house. And then they walk to this point. And they remeasure the angle of elevation. First of all, common sense, is it going to be bigger or smaller than 21 degrees? Yeah, just act it out in your head. Now I'm going to look closer to that spot. And if I was right underneath it, it'd be bigger. It'd be like 90 degrees, right? So it's only one answer there. As you move closer, this angle is going to increase. And you could be given a lot of different information. Maybe you know the distance you walked, 200 feet. So pretty challenging question there, but it is possible. So we want to break this up into multiple triangles. Again, review back in your homework. I'll let that go. Another common question is something like, oh, I'm washing a building and I look at this building with an angle of elevation. This is the top of the building. I look down over here. I see the bottom of the building. So some angle, some other angle, I'll call it that. And you might know how tall you are. You might know the distance between the buildings. That's what I mean. Knowing how to set up a picture is important, and then knowing how to interpret the question is also important. And that's the problem solving piece. Like actually being able to think about a question and apply it is part of what mathematics teaches us. Logical thinking. You can't just come in and say, I want a formula for that. Not at this level. Okay, so there will be some problem solving in terms of word problems. There, let me see if I'm missing anything. I think I got it all. Oh yeah, sine graphs. Thank you. Yeah, that's a big one. Sinusoids. And this is where it ends. So y equals, it was there, so I was telling you, it's right here. Last thing on the list. State amplitude, period, phase shift, So I would have got it. Right? Or y equals a cosine b x minus c plus d, aka your most recent homework, the one that was due today at 4, which you can is now in late period, but get that done. And yeah, so I'm just giving you like the highlights: amplitude, period, phase shift, and midline. Homework questions, right? And that's literally what I did. I like literally, as I said, scale down the test. If you just listen to me carefully, you know what's on the test. I literally just told you what's on the test. No excuse. So it's been a couple. We had a spring break. There's a little vibe there. There was an element on the campus that caused anxiety. I happen to be out, so it's been a little bit rough. This is the most straightforward test I put forward. If you know these things and you do what I ask, you should have like it's on you, and I'm not trying to be a jerk. So you should feel super successful. There'll be literally no tricks. And that's it. All right. So first question will be a blank unit circle. I'll see you on. Yeah.
You didn't mention reactivity qualities.
I didn't. I'll send that out. It's there. You know what? I'll cut it. Yeah, because you know what? I'll cut it. I'll cut one more question off. Easy. Easier. So I can do that easier than having to like backtrack it. Yep. I'm fine with that right now, to be honest. It's one small. It's important, but like in the grand, we have enough. Everything I said's on the test.
Yeah, I know.
So interesting point here. We were talking about the domain of your sine, cosine, tangent. For my real world applications, like we cut sine from different.
Do you?
We cut it from 90 degrees to 270 degrees.
But then you have an overlap, don't you?
No, it's almost like a transformation.
90. You have negative. Okay. Yeah.
So it's basically like a
So you have positive y's and negative y's.
The reason is because when we're using it to measure electrical signals, right?
Yeah.
You have the telescope, the big.
So you're doing this. You're doing this interval.
This interval.
Okay.
Because we can't detect.
Oh,
negative
negatives.
electrical signals.
Interesting.
So we
Oh,
cut
that's
it from
cool.
high to low and low to high. And we basically use cosine and sine interchangeably because they're just transformations of each
Right.
other. And we differentiate the signal whether it's a ratio of tan versus a straight signal of sine/cosine, whether it's downward facing or upward facing, because you can't emit an inverse of a signal function.
That's cool.
Yeah.
That's very cool.
We're studying this right now.
I love that.
We're studying. You can understand this.